In this video, we will see about retarded potential. The antenna analysis can be started with the retarded potential actually. So retarded means delay. So when you have a conductor in which some time varying current is passing, and in order to analyze the situation, we'll assume some differential volume in this particular conductor. And this differential volume at the source point is available at the distance of r from the origin. So we assume this is origin. From this origin, the source point is available at the distance of r. And because of this current flow in the conductor, you will get the fields in the space. And you are observing the field at this particular point. And this particular point is having a position vector r dash. So position vector will be given with respect to origin. That is why this arrow I have given like this. Then the position vector of the source point is given by using this r. Then the distance between the observation point and the source point is, I'm considering like capital R. So as per vector addition, I can take r bar plus capital R bar is equal to r dash bar. So r bar is the distance vector between observation point and source point. That is equal to, I can write r dash bar minus r bar. That means you can remember it in this way. That is observation point position vector minus source point position vector. So like this you can able to remember this point. So what I'm saying is, because of the current flow in the conductor, you will get the fields in the space. And here we will take the potentials. Two potentials are possible. One is scalar electric potential and second one is vector magnetic potential. So the potentials we are observing at the observation point P. We'll assume the observation point is P. So at point P, we are observing these two potentials. The source is, for example, available at t is equal to 0 seconds. But the response at the observation point will not be available instantly. It will take certain time. What is the reason for this? The electromagnetic waves travel with light velocity in free space. So this C is 3 into 10 power 8 meters per second. So it is certain finite velocity. Because it is a finite velocity, it will take certain time to reach the observation point from the source point. There is time delay between response and excitation. Okay, so immediately instantly we cannot get the fields at the observation point. There is a time delay. that itself is retardation. Corresponding potentials are retarded potentials. Now we'll see the expressions in a short manner. We know that electrostatic potential due to point charge V is equal to Q by 4 pi epsilon into R. Because it is potential, I can tell volts are the units. You see how this particular equation is giving the information. Q is a source. Then how you need to observe potential is proportional to source. R is the distance. So V is inversely proportional to 1 by distance. Then you keep on seeing, starting from the Coulomb's law, in the electric field, so you will be having 1 by 4 pi epsilon. So by observing all these points, now coming to the expression for V only, but not due to the point charge. The charge configuration can be anything. Now we can write the expression for V. V is equal to a charge is to be placed because source is a charge. But now the charge is changing with respect to time and space also. So, and total charge I need to write. The charge configuration we know that may be point charge, line charge, surface charge, volume charge. The diagram we have represented it is the volume. Differential volume dV within that one this differential the volume charge density rho v is available. But how to get the overall charge? We need to do integration of that one. So now the equation can be modified like this: integral rho v dv by 4 pi epsilon into the distance is r. But the charge is not fixed. Charge is changing with respect to time and space. So rho v is a function of distance and also with respect to time. But here I am representing the delay. Already I have told the response will not be coming immediately, instantly. So there is a delay because of the finite velocity. There is a delay. The delay we can represent with the distance by velocity like this by, and here dv, then by 4 pi epsilon into r. This is the expression for the scalar potential. Now we'll see vector potential. So magnetic vector potential A bar. To write the expression for this one, just I am recollecting the expression of the scalar potential what we have written previously. V is equal to integral rho v is a function of time minus r by c, comma is the function of r also. And here dv by 4 pi epsilon r. What I told you while writing this particular expression, V is proportional to source charge. V is inversely proportional to distance. And everywhere we will get 1 by 4 pi epsilon. So the response is the potential. Potential should be proportional to the source. Okay. And whether it is a scalar potential or vector potential, that it changes with respect to distance. Okay, inversely. So by keeping all these points in the mind and about 1 by 4 pi epsilon, we can think like this. In the electrostatics, you will get 1 by 4 pi epsilon. In the magnetostatics, you will get mu by 4 pi. So here epsilon is the medium property, here mu is the medium property. So permittivity epsilon is the ability of the medium to store the electric fields. It is the permeability of the medium, okay, which is representing the ability of the medium to store the magnetic fields. 1 by 4 pi is common. So how to write the expression for now potential, magnetic vector potential A bar is equal to, and we know that current is the source for the magnetic fields. So instead of charge here we have to keep current J bar of. Again same thing. It changes with respect to time and space. Here dV by, here we can able to write 4 pi, but mu will be coming in the numerator and R. Like this we can write the expression for this particular A bar. Okay. So this is the expression for V and this is the expression for A bar, that is magnetic vector potential.